Hello, everyone. My name is Hugh McKee. I'm with Lightbend. I'm a developer advocate at Lightbend, and in honor of my great host of this whole conference, I've never been to Israel before. It's a real treat for me. But I have one of the T-shirts on. But normally when I do this talk, I'm a huge Akka fan. So I traded my Akka T-shirt today for the Scalapino T-shirt in honor of this awesome conference. But today I want to talk to you about messaging in a microservice environment, and I kind of call it safe passage messaging in a microservice environment. And this evolution that's happening in the way we build systems, I think to me, it's really fascinating. And there's so many nuances involved in it, and particularly in the areas of things like building these new systems that are tough, that they can take a hit and they can keep running. To me, that's the biggest thing is building systems that just can really take a hit, not like a hit in reliability, something goes down, something breaks, and the system keeps running. You get a spike in traffic and the system keeps running. And it comes from things like DevOps, where I kind of grew up in an environment. I worked at HP in IT, and before we were even calling it DevOps, we were doing it where we were doing production support. So you pay for your sins, basically, in that you build something, you put it in production, it doesn't work, you get the phone call at 2 o'clock in the morning on Sunday saying, hey, we're down, we got to get back up, and those are not fun places to be. So I think it's the best experience you can get is to do that kind of DevOps type of support. But before I get into the messaging part, just want to briefly talk about some of the there's this whole thing of modernization, and we're kind of getting deeper into it now. When I first started doing this talk, it was a little bit more early days, like last year. This year I think things like modernizing is just taken as a given, and many of you are already doing it, are well on your way. But I keep running into a lot of people that are early in their journey, and there's just this massive change that's occurring in the way we build systems. And it's kind of driven by, at least, there's many factors, but I think it's, in some cases, it's really these three things: customers, business, and just the sheer volume of traffic, and the things that we're throwing in our systems are just going way, way up. Like everybody spends their day, almost everybody spends their day in glass, right? We're just staring at glass all day long. It's your phone, it's your tablet, it's your PC, it's whatever. We're always on systems. And if you think about it, the majority of our time that we spend on these systems are on the big systems, like Facebook and Twitter and LinkedIn and so on. These are systems that are just built to handle very, very high volumes. And occasionally, we as users, or the users, come into our systems, and their expectations are the same. They expect super fast response. They expect the system to be up all the time, things like that. I have a wife and daughter who their patience is razor thin. If an app doesn't respond correctly, they complain and whine and cry, and then they're gone, and they probably won't come back to that app. That's the kind of things that we're dealing with. Same thing is with the business. The business wants to move fast. Most of my career was building systems with 6-month cycles or year cycles for deployment, which is insane these days. It's more like, hey, somebody has an idea on Monday and they want it in production on Wednesday. We're moving very rapidly into that kind of a world. And at the same time, it's just the demands on our systems, what we're doing with things is just growing massively. I think one of the most interesting areas is like IoT, where there's devices everywhere. And in particular, we're seeing this a lot in the Akka space. Akka is a really nice tool for building IoT type systems. Akka is, if you haven't heard of Akka before, I think many of you have, it's the actor system on the JVM, which I absolutely love. But in any case, there's just all these interesting things that are happening that, in a way, it's like, for many people, and I see this all the time, it's like, oh my God, how are we going to handle this stuff, right? What are we going to do? Everybody's saying we got to do all these new things, and everything that we were doing before is obsolete, everything's changing, how do we keep up? But so it's kind of this scary thing. It's like, let me just hug a tree for a while and scream for a bit. But in reality is that I think that we're very quickly learning how to build these new kinds of systems. And the way I kind of look at it is that we're entering this architectural renaissance that's marvelous. I mean, I've been doing this stuff for a long time, and today what's happening is so much more interesting than anything I've ever seen. It's just absolutely incredible. And I think it is this renaissance that's occurring, there's very significant changes that are occurring that, that if many of you are doing and many of you want to do. And we're all on this very, very rapid journey where things are just changing so fast. But in many cases, when we're talking about modernization, it starts with the monolith. How many people recognize the movie that this picture's from? Oh man, not a lot. It's 2001. Sorry, yeah, 2001. It was 50 years ago today, or this year, that that movie came out. I can't believe it. I just watched it again recently, and it's still incredible. As far as the tech and everything, I was enamored with it with the tech and everything when I was young and saw it. But in any case, we start with the monolith. And often people think of the monolith or think of modernization as modernizing the code. But to me, just as important is modernizing the data. And we're starting with monolithic systems, monolithic code. And also, I think the bigger nut to crack is the monolithic databases that many systems have. So sometimes I've heard other talks where they talk about monoliths as a big ball of mud, which is kind of a derogatory term, but I don't really agree with that because, we know how to build monoliths. There's marvelous tools to do it. We've got a lot of years of experience to it. Pretty much all of us have probably built and worked on those things at some point. There's still viable technology, but there's things like we can scale them to a certain extent and so on. But the challenge is that I show this, I just drew this graph, but I call it the Goldilocks zone, where you want to build systems that have the processing capacity where no matter what the spikes are, the increases and decreases in traffic, that your system is always has sufficient capacity to handle it. The really bad place to be is here, where you have some kind of a spike in traffic. It could be seasonal. Like the biggest shopping day in the world right now is Singles Day in China. There's massive spike in transactions. So all the systems, all the retail systems that want to play in Singles Day, and this is like Black Friday, and Cyber Monday and things like that, they have to be able to handle these huge spikes in traffic, many, many orders of magnitudes in some cases, spikes in traffic. It gets hard to do that with the ways in the past that we've been building systems. This is why we're searching for new things. The simple fact of the matter is that we need to build systems that can scale, that can do a lot of things in parallel. And part of the fundamental law here is like Amdahl's law. You only get so much capacity or so much processing power out of the ability of your system based on its capabilities for parallelism. As you can see, if you have a system that's 50% of it can be parallelized, you barely get any performance improvement when you throw more capacity at it. You got to really get up there where you have lots of parallelism before you can take advantage of it, but it still flattens out at some point. So the challenge that we've been, in many cases, like I grew up in an enterprise environment. Lightbend, we focus a lot on enterprise customers. And to me, whenever we had performance issues, it was almost always related to bottlenecking on the database. And often the database was a single point of failure. We could do lots of things with the code, but sometimes there was only so much we could do with the database before we hit that ceiling. We couldn't go any faster. So there's this whole process of modernizing the monolith, and I don't know what you guys are doing, where you are all on your journey of doing things maybe differently. I know, like Wix, for example, you guys are leaders in this. Everything I've seen other talks that you guys have done, and I think you're a leading edge type of company. But there's a lot of other companies that are just starting on this journey or part of the way into it, and they're learning how to build systems like this. And this is what this talk is really addressed to. So one approach is that you take a monolith and you start carving off pieces of code, and you start introducing microservices. Now, I've heard this called the distributed monolith or microlith. So you can, at the code level, you're talking about things that, oh yeah, I'm implementing microservices. And often when I talk to people, I ask them, what kind of system are you building? And you say, oh yeah, we're doing microservices. And I dig a little bit deeper. And they're often doing this, that they're building microliths where they've cut up the code, but they haven't cut up the data. And the challenge there is that, well, you still have contention probably at the database level, and you still have a single point of failure. So this isn't a bad thing. I'm not saying this is a bad thing to do. It's a step in the right direction, but it's a step along the path of the journey of moving towards the kind of, as close as you can get to the nirvana that's promised by some of these new architectural approaches. So the idea, though, is with microservices, the fundamentals are you want strong cohesion on the inside and loose coupling on the outside, which means, and I want to emphasize this because the strong cohesion part is that you only put things in a microservice that belong there. So it's like a microservice should do one thing, right? And it should do that one thing really well, and that's it. And the coupling should be, and it's as loosely coupled as possible at all levels, not only at the way it integrates with other microservices, but it's in the development phase as well, that if, say, you and I are working on a microservice and everybody else is working on some other microservices, we shouldn't have to keep going to these other teams asking them, can we do this, can we do that? Because if we're using the same database and we want to make some change to a database, guess what? We got to go to the big meeting. We got to talk to everybody and say, is it okay if we make these changes to the table, which takes time and slows you down. That's tight coupling. So you're coupled all the way from the development process up through into production. So you want to minimize that coupling as much as you can. So I kind of have three little guidelines, I guess, or questions that I ask people that when they're doing microservices. So I ask, all right, so you're doing microservices. This is the easy one, are they independently deployable? And then they go, oh yeah, man, we got CI/CD, everything's cool, and we can push it out in production pretty quick. It's like, awesome, that's great. Do you own your own schema? And this is often where the wheels come off the apple cart, as they say, right? Because especially, if you're in a startup or you don't have a lot of legacy code, then you probably don't have an issue with this. But if you're in an enterprise, enterprises have a long history of taking databases very, very seriously. And going to get permission to break up some big old legacy database, I don't know how many of you guys are working in enterprises, but if you're there, that's where I came from. It's like, wow. It's not an easy process. I'm actually working with a customer in a legacy environment that wants to modernize, but it's a new adventure every time we go to do things like, oh yeah, we want to create this table. We want 2 databases. What do you mean you want 2 databases? Things like that. These are all new things that the enterprise teams are struggling to try and understand. And then the third thing is that the only way to get to the data in your microservice is through the API. So to give you an idea of how seriously some companies take this was an excerpt from an email sent out way back in 2002 at Amazon. So basically, this email said, the only way services are accessed is via a service interface or through its API. There's no backdooring. No other forms of communication are allowed. And you can read the other parts of the message, but if you look at that very last part, anyone who doesn't do this will be fired. So it's like, they took this really, really seriously. And this is back in 2002, before we were even talking about microservices, but they basically kind of were. And I think it's this discipline in software engineering that's contributed significantly to the success of Amazon at the enterprise level. Pushed them into the cloud. I was at HP, a hardware vendor, and I'm watching a bookstore basically become the supreme cloud provider of the universe, right? And it's like, why are hardware companies sitting there not getting it, and this bookstore, this online store gets it? I think it's because they had a strong discipline of engineering. So the idea is this reduced coupling allows you to build systems that now all of a sudden architecturally are more resilient. Things like if you're building a system where you lose a microservice and the whole system itself is still up. That's part of the goal. But these microservices are, they're not this neat little matrix that I have on the left. It's more of this kind of messy network diagram, kind of thing on the right, where you've got services that are talking to other services in some form or another. There's some exchange of messages and so on happening between all these microservices. So as an example, there was this really good article. I don't know if many of you may know this guy, Chris Richardson. He's got a website called microservices.io or I think it's microservices.io. And anyways, he's a well-known speaker, and he's a frequent writer, and he wrote these two articles, I think it was last year or the year before, called Developing Transactional Microservices. And it was two parts. I really enjoyed these articles because in this article he talked about the kind of exchange of messages between a customer service and an order service. So I want to walk you through this exchange. So we had these two independent microservices, say order service and customer service. We have this, we build up an order, and at some point we create the order, okay? That's a transaction, it's done, right? We captured that. After that transaction is completed, we want to communicate to the customer service that the order has been created. The customer service gets that message, and its job is to reserve credit for that customer, say, in this example. So it performs another transaction. And depending on the outcome of that, say the customer has sufficient credit or it doesn't, the customer service responds back to the order service saying, all right, say the customer's credit is good and we've reserved the credit for this customer. And then finally, the order service gets it back and it changes the order state from new to approved. So it's a third transaction. Now, in a monolithic world, this would have been done as a single transaction. Now it's broken apart into 3 transactions. And we have all these interactions going on, essentially asynchronously, not locked in time, where we're performing these different operations. And this is where things get really interesting. When you build services like this and you have these messages that are going back and forth, and this is just a simple example where you can see that if we were to lose the exchange of messages between order and customer, the result would be we'd have orders stuck in a new order state, not moving forward, right? And the system can't, that's unacceptable for the system. The system has to be able to move these orders forward. So I want to just kind of throw this out right now and think about it. We'll come back to this in a few slides, but would it matter if this is these messages that are exchanged between the order service and customer service is done asynchronously or synchronously? Would that impact the reliability and scalability, but particularly the reliability of these services using one approach over another? So at first, this looks really scary. I mean, I couldn't find a scarier bridge picture. This one's pretty scary. You got this wild river and this kind of looks like fairly strong bridge, but it's not the strongest bridge. Some people I think would be scared to walk over this bridge. But on one side you got the order service, and the other side you got the customer service. And the point I'm trying to make here is that the exchange of messages between these two guys is precarious. Things will break. Things won't work all the time. And how do we deal with that when we're building microservices? The thing I want to kind of get across to you is that it is possible to build a bridge between services that is stronger, that will work, and the goal really is that you have messages that never get lost, that the system can always, under any circumstance, no matter what's failing, no matter what the load is, can get messages across to each other. So really the thing to ask is, when you're building something like this, is what will go wrong? And I often tell people, people that I work with, this team I'm working with right now, I say, this is just semantic, but think about it hard. Don't say if. If this breaks or if this happens, say when. And if anything, if you take away anything from this talk, just remember that when you're working on services, think of it as in terms of when this breaks, what's my service going to do? And you think about the worst possible failure scenario, because I can guarantee you it will happen at some point. And too often people build services for the happy path. And it's really easy to think through, all right, here's the exchange of messages and everything's happy and we're good. But then you're in production and all of a sudden, hey, we dropped some messages. And a customer starts complaining, hey, my order's stuck in a new state, it never moved forward. And then the business gets it, goes, hey, we got customers that are complaining, stuff's not working. And then your management comes to you and says, hey, you idiot, you got messages that aren't going through. And I had this one system where we were trying to synchronize some stuff between two things, and we would get millions and millions and millions of messages right. But every once in a while we drop one. It was like a fraction of a % of the messages would fail, and it was the bane of our existence. It was, have you fixed this problem yet? Have you fixed this problem yet? The business was beating on us. Our management was beating on us. It was not a fun place to be. So what will go wrong, for example, is things like, the obvious, the order service can't talk to the customer service for some reason. The network's broken, the network's slow, something's wrong there. But then there's more subtle things like the customer service got the message, but before it could act on it, it failed. Or even better, it keeps getting better. The customer service got the message, did its thing, but before the response got back, something failed again, and it didn't make it back to the order service. And then finally, you even have to consider, the message made it all the way through the whole round trip, got back to order, but order died. Something happened to order to prevent it from performing the service. So it's all these things can go wrong. So in the case of asynchronous or synchronous, the way I kind of look at it is like there's, in this little example I've been walking through, there's like these 5 steps, right? At the start, we make some kind of decision, perform some kind of transaction. That results in sending some kind of request over, which triggers another reaction. This is step 3. Step 4 is you get a response back, and step 5, you react to that response. Anywhere along that journey, things will break. It's not if it will break, it's when it will break, and what are we going to do about it? So does it matter if it's asynchronous or synchronous? And often I see people using synchronous, thinking that might help them, and often some people use asynchronous, but the fact is that it doesn't matter if using synchronous or asynchronous is not going to help you in the resilience part of this. It's not going to help you in all those failure scenarios. It just doesn't matter. The other part of this is that say goodbye to ACID, right? Many of us grew up on these really comfortable transactions. And database transactions are a marvelous feat of engineering. And all of a sudden, they're kind of ripped away from you where instead of one big single transaction, in the little example I gave you, we were doing 3 individual transactions that have to happen in order, and we can't break that cycle. So how do we deal with that? Now, in the last talk, the speaker mentioned chaos engineering, and I just want to talk briefly about this, but how many people heard of the Simian Army at Netflix? Pretty good, yeah. Basically what this is there's a team whose responsibility is at Netflix is to break things in production. And the thing I think is most powerful about this is the psychological impact it has on us as developers and us as architects, in that instead of going into production thinking, well, we might have this problem, we might have that problem, now you're going into production with this evil team that's going to do everything they can to find weaknesses in your services. So it's like this battle between the chaos engineering team and us. We got to build these systems that can stand up to all the chaos that they're going to throw at it in production. So I think the result is that it's that kind of an approach that hardens you, that just brings to reality when things break. When that team breaks the network, slows the network down, takes down one of our servers, how is our service going to respond? You have to think about these things these days. The days of not doing this kind of thinking are beyond us. And it gets even more interesting. Like many of you guys are moving to something like Kafka, and Pulsar is another one that's really interesting for a message bus. And they do much more than that, but fundamentally, one of the things they provide is a message bus. But in this picture, what I kind of want to point out is that once you get a message into Kafka, say, it's going to get to the other side. But there's this little stairway, like in this plane here. You perform a transaction in order, and then you got to push something, you got to make a call into Kafka. Well, that's not part of your transaction. That's a point of vulnerability. You could be walking up those stairs and fall down. And then what are you going to do? It's going to happen. What's your system going to do when that happens? Likewise, it's on the other side of the journey. You already got to the other side. You're pulling that message into your application. Well, in many cases, you're performing a transaction that's not part of Kafka. How do you make sure that every single message that Kafka gives you, you consume and process correctly? And there's these little gaps, periods of vulnerability is the way I think of them, where you've got to think about these things. So for messaging, there's the kind of two fundamental approaches. One is push and one is pull. The most intuitive one is push. I'm writing some code, it's creating an order. All right, the order is created, now I want to make push my message to the customer service. Right? That's my intuition kind of drives me in that direction. It just seems to make common sense. However, often the pull approach is a better approach. We're going to look at both a little bit here. But there's in messaging, there's three forms of messaging basically. There's at most once, at least once, and exactly once. So I like to think of at most once as maybe once. If it's at most once, some messages make it, some don't. Akka, for example, the messaging between actors is at most once. So when you're building Akka systems, you have to take that into consideration. At least once is once or more, though. And this is the best, I think. When you want a reliable system, you have to have it at least once type of messaging, or once or more, which means that any individual message will get delivered, but it might be delivered more than one time. So the consumer of those messages have to take that in consideration. You're going to get the same message maybe more than once. And there's a kind of the mythical, I think, exactly once, or some people call it essentially once. But when you really look at end-to-end messaging, just because when you're in a distributed systems environment, exactly once is almost like breaking the speed of light. You're breaking a fundamental law of the universe. It's just not going to happen. There's people that talk about exactly once, like Kafka came out with an exactly once messaging, but they were very upfront about it, and they were very clear about how they implemented it. And basically, what they're doing is they have at most once, but they're filtering out the duplicates, so the consumer is not seeing the duplicates. So it's a little trick that they're playing that gives you exactly once, which is very cool, but it's end-to-end messaging exactly once is, forget it. It's like, I just saw another article about two-phase commit just in the last week or so, and, because we'd love to have two-phase commit in a distributed environment, but it's, practically an improbability, and this guy was talking about just using two-phase commit, and where they found that it's essentially, it had periods where there was some messages didn't get through in certain cases. So even that is kind of something hard to deal with. So the situation is that there's plenty of places where your messages are flowing where everything's great, but there's plenty of places where you've got what I call these non-transactional gaps, these little places that come up and bite you and get you and drop a message every once in a while. And these are the ones you really got to compensate for. And it's even in the situations where you're using Kafka, don't let you got to make sure when you implement something that you think through single stage of the journey of a message. And it's things like, my code's calling Kafka. Well, that's not a part of transactions, so what are you going to do when that call fails, right? You got to think about that because you're in a kind of a non-transactional gap there. And again, it's like, you just performed a transaction, you posted something to the database, and now you're making a call to Kafka. Period of vulnerability, right? A non-transactional gap. How are you going to compensate for that? Doesn't matter if you're pushing it to Kafka or Pulsar. So with push versus pull, with a push approach, basically you're going to have something where you have some form of reach out logic. And so you try and send a message, and the message it doesn't get sent correctly. You get some kind of an error saying, yep, this one didn't make it. Now you don't know what happened to it. All you know, because you can't know what happened as the message went over the wire to another machine. all you can know is that some failure occurred. Maybe it was a timeout, maybe it was some other kind of an error, whatever. So you have to have some kind of a retry. So basically you're kind of building up a little list or somehow of messages that need to be sent. So you have to think about that. And this is even in the case, again, where you're just pushing something from your app into Kafka. It's the same kind of thing that you have to think about, this non-transactional gap. So a common approach that works better, I think, in most cases, is pull, where it's the consumer, not the producer, but the consumer that's responsible for pulling messages. So the producer is just, say, creating a list, a journal of messages that is created. It's the consumer is keeping up, trying to keep up with offsets to try and keep reading things from the pending messages list. There's some big advantages here. There's things like it really simplifies the code on the producer side, because the producer just needs to dump things into a list. The consumer side, the consumer could go down and come back up and catch up, right? You're not having to deal with retries and things like that. And again, this applies for Kafka on the other side, both sides, where this is the approach. And in fact, this is the approach that Kafka uses. A consumer from Kafka uses this offset approach. This is why they're doing it, because it's a good approach where you're not going to lose any messages. So I want to quickly get into event sourcing and CQRS, command query responsibility segregation. How many are doing this, or how many? So it's pretty good. How many are familiar with it? Yeah, is it okay? I think this one's controversial. I've had discussions with people inside Lightbend who have been adamant about not pushing this too hard. Smart engineers. But the more I've seen it in use, the more I've worked with people that are using it, the more I've talked to other people that are using it, it just seems to be a very powerful architectural pattern for handling persistence. There's whole talks on this. This is a really, really interesting area. If you're doing microservices, this is definitely something to get familiar with. I can't do it justice here in this talk. But it really fits well. The only reason I'm bringing it up here is it really fits well with giving you the foundation for doing reliable messaging. Because guess what? That right side, that event log, there's all your work. The consumers need to pull from. So with a command CQRS, command query responsibility segregation, it's a separation of the writing of data with the reading of data, where when you're, say, creating an order, what you're doing is you're add shipping, add billing, add item, adjust item, remove item, delete the order. All these things are captured as events in a table. On the read side, you're storing data in a way that's optimal for querying, which is often in denormalized data structures. Their data structures are optimized for queries, not optimized for writes and reads. Like with a single database, one of the trade-offs that we've had to deal with is that you're playing a balancing game between optimizing for writes and optimizing for reads. This is a way to address that. The event log is really, really fast. It's just insert only. And then the query side is optimized for queries. Now, another guy that I think is really interesting, if you're interested in this stuff, his name is Pat Helen. He's wrote a bunch of different papers. One of them was Immutability Changes Everything. And in this paper, he wrote this statement that just blew my mind. He said, the truth is in the log. The database is a cache that is a subset of log. And when I read that, it took me a while to kind of internalize it. But when I read that, it was like, oh my God, I've been using these darn relational databases for years. And it gives me the cache of the log. Kind of always gives me the current state of my stuff. But internally, it's got this log, which has the history of all the changes. And now we're in this era of data scientists want all the data they can possibly get their hands on. And some of the perfect data for doing analysis is event logs, because not only do you have positive data, you have what I've heard called negative data. Things like abandoned orders, or orders that have the whole history of, oh yeah, they added this item to a cart and they removed it. The removal of an item from a cart is just as interesting, in fact, maybe even more interesting than the eventual order itself. So, the event logs are really powerful things to do that. Another one, he wrote this other paper, and he just said accountants don't use erasers, and it was like, that was like a mind-blowing moment for me as well. It's like every time we do an update or delete, we're basically getting our eraser out and removing data. And finally, he said, this one's a little old. He said for service-oriented architecture, which is old, but I think it still applies to microservices. Moving to microservices is like moving from Newton's universe to Einstein's universe. And his point is that in Newton's universe, in a monolith, you got these single transactions, right? And a database, it's a marvelous thing where when you perform a transaction, logically, it's like every transaction either happened before it, this transaction, or after it. So you're in this, when you move to a distributed systems environment, it's like moving to time dilation and relativity and all these different things. Just real quick, again, I'm from Lightbend. I'm a big fan of Akka. Akka has an implementation of event sourcing in CQRS. I'm going to just kind of quickly go through it. We've got the Play framework, Akka HTTP and Akka itself, and then there's a new framework called Logom, which is a microservice framework, and they're all built on top of Akka. So Akka, one of its other big claims to fame is that you can write clusters of, it's like you're not constrained to a single JVM. You can write a system where it spans multiple JVMs, but it behaves as a single system. So in effect, you're doing things like writing a microservice that is clusterable, its own little cluster of, say, containers running in Kubernetes or wherever. Because one of the other goals of going with microservices is you want to, again, create a system that's resilient. If a microservice goes down, an individual microservice goes down, the system as a whole keeps working. And what we're trying to do is take a step further where, say, you have a microservice that's running in its own little cluster. If one of those nodes in the cluster goes down, it keeps running. So just to get close to wrapping up here, when you get into this mode of absolute reliable messaging, which is achievable, then some new patterns emerge. And this one's kind of interesting to me. And so say you have this customer service where every time order or shipping needs to do something, say place an order or ship an order, it needs to retrieve some customer information. So you say, oh, no problem. Let's just do a RESTful GET to customer and retrieve the customer information. The challenge there, though, is that if customer goes down, its blast area is bigger, because if customer goes down, it has the effect of taking down those functions within order and shipping. So if you have reliable messaging, maybe you can reverse the pattern. So the idea here is that every time a customer changes, it just publishes, hey, I changed this customer. Order and shipping, for example, are consumers of those events. So they're keeping their own view of customer. So now, when ordering and shipping need customer information, they don't reach across the wire to customer anymore. They retrieve their own view of customer from their own local cache or own local persistence store. And that way they can do it a lot more quickly, but more importantly, you've really decoupled the services. And loose coupling is a goal, right? So this is a new pattern that I've seen. And a lot of people, the reaction is, oh my God, wait a minute, you're replicating data. And say, yeah, we are. We're replicating data. Well, that's expensive. It's like, no, man, disk space is cheap. It's a lot cheaper these days than it was not too long ago. So these kinds of patterns are now becoming possible, which means the system's more resilient, it's faster, there's less traffic on the network, on and on and on. There's lots of advantages to this, but it's counterintuitive. But that's the fun part of what we're doing, right? Is kind of tearing our brains apart and putting them back together and doing these new things. So how to evolve? If you're stuck with a monolithic database, maybe you can start chipping away with it. And what I mean is that, say maybe in the database you introduce event logs. And they're just another table in the database. And maybe you start adding this and you start incorporating those things into your microservices. And then maybe the next evolutionary step is that you start to pull the event log out of the database. But the flow is that every time something changes in the database, it goes into this event log. But then ultimately, you start reversing the flow, that first something happens in a microservice, is pushed into the event log, and then is pushed into the database. And then finally, you cut the string, and you're kind of in that fully independent, not only independent at the code level, but independent at the data level, where you've broken off your own database. So just to wrap up, there's lots of things that are happening in our space. One that scares the heck out of me is that the data volumes are just going way, way up. It's just, what that means for us is that we're going to have to be building systems that handle ever more stuff in the volumes that were incomprehensible just a few years ago. And we're on this point in the curve, and it's just going almost straight up on us just in the next few years. And last thing, I just saw this in an article from Werner Vogels from Amazon, the CTO of Amazon, basically saying that the days of one-size-fits-all monolithic database are behind us. Things are just changing. It may be behind us for them. I hope it's behind us for you guys. For many of you, it is behind you, then that's great. But if you're on the beginning parts of this journey, I think it's going to be a lot of fun. So it kind of comes down to just building systems that can take it and keep running no matter what. And to me, and this has been part of Reactive since the Reactive Manifesto came out 5 years ago, I think it was, it's all message driven. If you're interested in Naka, I wrote a little Riley book. There's a lot of other material, but this is kind of just an introductory thing. And thank you very much. We had time for some Q&A if you have any questions.
I have one, but it's a bit of a tricky one. What if your data doesn't allow for you to create this loose coupling? What if the data is the one that is tightly coupled?
Well, yeah, and that is the reality that for many people, right, that you can't break up the database. And like I say, if you can start to break up the code, it's definitely a step in the right direction. And then you just have to keep fighting the good fight to get, against the forces that are against breaking up the database. And in many cases, it's arming yourself, educating yourself on the advantages of doing it. This is why I'm such a big fan of event sourcing and CQRS, because it's like a shock to the system. It's such a radically different way of doing things, but the more we get into it, the more I think we're getting better at articulating why these things are the right thing to do. But I know it's a really hard battle. It's a really hard battle. Yes, sir.
If your database was once your single point of failure, how do you avoid your message bus becoming your new single point of failure?
Yeah. Excellent question. I don't know. The message bus is becoming so important. And Kafka is the big thing right now, but I've been looking on my own a little bit at Pulsar, and I think other things are going to be coming along. Pulsar looks really, really interesting. It's new, but it's got a good story, I think. But yeah, it's one of those things where you even there, it's like when you're building your services, when Kafka goes down, what are we going to do, right? You just have to face it, right? And it's not infallible. It's going to break. It's a reality. Take a deep breath and it's like deal with it, right? So it's things like the best place you could be is that you're building a system where, all right, Kafka goes down and messages can't flow. All right, can the system run at all when that's happening? Well, maybe if you've done some caching, that I was just talking about a little bit earlier, perhaps the system can keep going a bit, right? And maybe keep going and write it out. But at the very worst, the system should be able to come back up and catch up. Yeah, and you don't lose anything. That's the main thing. Architecturally, you implement something where Kafka broke, it went down, we come back up, and we know what happened, but did we build a system where we didn't lose any messages? Then you're good. All right. Thank you again.